Okay, now welcome back everyone. Today we'll be talking a little deeper about some complexities of determining internal forces within beams. So I'm just going to use these beams just to explain some concepts that I will be going through today, and then you can apply them to different beams that you encounter, and then we'll try to see if we can do an example. Now, understanding internal forces is crucial. It's very important for designing structures that are not just strong, but are also safe and reliable. Now, when we talk about these internal structures, we're talking about the internal forces and couples that are exerted on a portion of a structure by the rest of the structure. Now, if you look at this beam, we will have some external forces like this applied forces and the support reactions that will come from this supports. Now, internally inside this member, which is our beam, we do have some resulting forces because take a portion of this beam and say that we have a section here of a beam, and then we have some force that is being exerted on a beam. Let's say that applied force is applied axially and it's pulling outwards from our member. Now, this is just a portion of a beam. Let's say I cut it somewhere and I just took a piece of the beam. Now, this section here, let me actually do this to show that I cut it. Now, this will represent the inside of the beam, how we will visualize the internal reactions within our member in this instance. Now, we spoke about equilibrium and saying that even in Newton's laws, we say that when a force is acting on a body, there must be some reaction that balances that force, that acts in by the same magnitude, just in the opposite direction. Now, even if I cut a section of this beam, it wouldn't make sense to just have a section of this beam and just one applied force that goes into one direction. Now, intuitively, you would see that if this force is left alone, then this section of the beam will start moving that direction, will be displaced in that direction. Now, internally, it will experience this force. There will be an effect here. We will see that the effect of that force, because internally there would be a force that tries to react to that external force. Now, it will act in the opposite direction by the same magnitude, because what we are looking for here is equilibrium, and that is very important. Now, in this instance, we looked at the axial internal loading, because there's an axial force that is acting on the member. Now, because this force of mine is perpendicular to the surface of my cut here, we are going to call that force the normal force. Now, this normal force acts perpendicular to the surface of your cut. It will, because of our axial forces, there will also be an axial internal loading. Now, even if we were looking at an effect of a force like this one of 110 kilonewtons, but it is at an angle, it would have a component that is acting axially. So it would have an x component, horizontal component, that would be pushing in a x coordinate direction. Therefore, we would have an internal normal force that is acting on our member. Now, we'll look at more example to see how it will react to different type of forces. Now, also, because in some instances we will have some forces that are acting horizontally. Now assume that there's a force that is coming at this direction. Now because this force is acting upwards, you would assume that to get equilibrium there must be some internal, I don't want to call it reaction, but let's say there will be an internal effect that will then say we have to balance out this force. Now this force can act at anywhere within the length of our beam. Now internally, if you look at the section of our member, let's say if there's a force that is forcing a movement in the horizontal direction, now in here there will also be an internal loading that tries to balance off that external force. Now because here our force is acting in an horizontal manner, even inside here we will have a force that is acting in a horizontal manner. Now because it is trying to cause movement horizontally, the resistance in here will cause a shear, will cause some shear between this member and this member. Now hence we call this force the shear force. Now let me write it. The shear force, because of the resistance that will be in here, all the friction that will be trying to resist the motion of this member moving horizontal. Now this is called the shear force. Now let's say in another instance we had a force that was causing, we had an external loading that was causing some bending in our member. Now if you have a member and it is experiencing some bending in this sense, let's say we were seeing some sort of bending in this sense, now our member here would feel that effect, will feel that bending inside and try to react to it. There would be an internal effect that takes place inside our member as a result of the external bending. Now as our member bends like this or even in the other direction, we therefore inside here have an internal moment. Now this will be our moment. Now in some instances, people have asked what's the difference between moment and torque. Now, moment is an effect of bending. Now, when there's bending and our member tries to resist it in here, it will feel that effect of external bending, and then we'll have the moment inside that tries to I don't want to use equilibrium as a verb, but that is ultimately our objective. Now, the moment the force that is inside to resist the bending is called a moment. Now, with the instance of torque, torque basically causes spinning. Now, if there's a member here and then it rotates in some sense, then we are talking about torque. The formulas may be similar, but the effect is different. Now, also another thing that is called torsion. Now, with torsion, you can visualize it as a sort of twisting that happens to a member. Now, if you take my ruler here, and then this side I twist that side, and this side I twist this direction, then you experience some sort of torsion. Now that's how you differentiate between what is moment, what is torque, and what is torsion. Now that we know the normal force, the shear, and the moment, these are the three that we are going to focus on. Now remember that normal acts perpendicular to the surface of the our card here, but mainly it is to show the effect of the external force that is pulling on the member axially, making it stretch. Now, when there's an axial force, then we'll have a normal force inside. Now, I'm going to denote it by using the letter N going forward. Every time you see this in this video, we are talking about normal force. Now, the shear force, I'm going to be using V because I'm used to that. And the moment I'm going to be using a capital M. They are all capital letters. Now, the sign convention that we're going to use for these axial forces, the shears and the bending moments, is crucial. It's important because it ensures consistency in terms of interpreting internal forces. Now, also, you must notice that in this conversion, the internal forces are considered positive based on their effect on the beam. Now, for instance, if we look at our axial force, it will be positive when the external force tends to pull the beam apart. Now, this is this case when our external force tends to pull the beam apart, we will then look at the internal axial force as positive. Now, with the shear, we will take it as positive when the external force tends to push a portion of the beam upwards. And then in terms of bending moment, we will take it positive when the external forces tend to bend the beam concave upward. Now, let's start talking about the analysis procedure, how we're going to actually analyze this beam to find our internal loadings. Now, the first thing that we're going to do, as you can see here, I've magically put a free body diagram of our beam, our free body diagram. Now, I want to visualize my beam so that, because firstly, I have to compute the external support reactions. Now, I have my force here, 135 kilonewtons, and then I have my force of 110 kilonewtons acting at an angle. Now, I'm just going to name my points here as A, and then I have B there, and then I have C. Now, also here, I have A, I have B, and I have C. Now, how are my support reactions going to be like? Now, the first thing that you should know is that with regards to support reactions, when you have a roller, it is only providing support in the horizontal axis. Now, if this beam was loose and only being supported by this part, it will be able to move in the x directions and it will be able to rotate, but it will not be able to move down because the roller is supporting it in that sense. So I'm going to put my support reaction here, which is at C, and I'm going to put a Y because it's acting in the Y axis. Now at A, I have a pin, and that pin, it is supporting our beam in the Y also. So I have A, Y, and also because it is a pin and it's pinned to this beam, our beam is not able to move in the x-axis. So for now, I'm just gonna put my AX. The direction does not matter. You can put it as pulling. The calculation will tell you which direction it is acting in. Now that I have my support reaction, I have to compute now and calculate how much they are. Now, let's suppose here I had a 3 and a 4. I had a 4 and a 3. Now, I look at my thing and I just try to see which one would be able to be simpler to solve first. And I have decided that I'm going to go for the x-axis first. Now, in terms of x-axis, we have to decide which direction is positive first. Now, in this case, I'm going to take my going to the right as positive. And with regards to equilibrium, you know that the sum of all forces in x must be equal to 0. Now, which forces are those? Now, in x, I will have ax, which is acting in that direction, so in this case it will be positive. Now, as I said, I could have written it as acting in that direction, and then in my computation I would have to put it as negative because I have decided that direction will be positive. Now, this is arbitrary. You can decide to make that direction the left as positive, but make sure that you reflect that in your computation. Now I have my AX, which is acting in the x-axis, and the other force that is acting in the x-plane will be our the x component of our 110 kilonewton force. Now, how do we find that? A lot of people can just put 4 out of 5 multiplied by 110, but I prefer to compute the angle here first and then use that in my calculation. So I have the opposite side and the adjacent side, so I will use tangent. So tan theta is equal to 3/4 because the opposite over adjacent, and I'm looking for this angle here. Now my theta will be equal to tan 3/4. So my theta is equal to, so it will be 36.87. So I will take that 36.87 degrees. Now that I have an angle there, I can tell that my x component of my force will be equal to 110. Because it is adjacent to the angle, we are talking about the x component, it is adjacent to the angle, therefore we'll have cos 36.87 degrees. Now also we must now look at the direction. Because our force is acting at this angle, we can see that our x component will be acting in that direction and our y component will be acting in that direction. Now, because it is going against our sign convention here, it will be negative because it is acting opposite to what we decided is positive. So I will have a negative 110 cos 36.87. Now, those are my only two forces that are acting in the x axis. So they must all be equal to 0. Therefore, AX is equal to, you transpose that and move it to this side, and then it will give you 88 kilonewtons. Now, we have our AX, which is this one, is equals to 88 kilonewtons, and now we have to solve for AY, and we have to find our CY. To find our AY, I'm just going to use, I've already used our sum of forces in the x-axis. What else do I have? So I have the sum in the y, but then I have two unknowns. So that is not yet useful for me. So what I can do is that I can use the sum of moments in our beam. Now, we first again have to decide on our sign conversion. That means that I have to decide which direction is positive. Now, I'm going to take anti-clockwise as positive, and then again say that the sum of all moments must be equal to 0. Now, another important thing here is that we must choose our reference point, our point of rotation. Now, which point is that? In this case, I have AY and I have CY that are still my unknowns. If I want to find AY first, I'm going to eliminate CY from the computation. So the only way that we can eliminate CY is by making it our point of rotation, because a force acting across our point of rotation will not cause any moment. And that is important to always remember in structural analysis. a force that is acting across, even if it was acting at a distance, as long as it goes across the point of rotation. Example, this AX, it is acting at a distance of 4, 6, 8, 12 all the way here, but because it is across the axis, the plane of our rotation, it will not cause any moment. Now I'm gonna solve AY first, so I'm gonna use CY as our point of rotation. So it is the sum of all moments about point C must be equal to 0. Now, which moments are those? Now, the first one will be caused by AY itself, because if I take C as my point of rotation, this force AY that is acting on our beam upwards will cause a rotation or bending in the clockwise direction. Now you can sort of visualize it and say, if this is our point C, this force at A will cause bending or even rotation about C. So I will take my AY. So I will take my AY, and then remember, you must multiply it by the distance where it is acting. Now from our point of rotation, the distance to AY is 12 meters. So AY times 12, it is the moment of at A about point C. Now it is negative because we said that positive is anti-clockwise, but since this sort of bending or rotation will be clockwise, then this entire magnitude will be negative. Now, where else do we get a force that causes a moment? Now, 135, our 135 force that is acting in the y-axis. If you are at C, again, let's visualize it. About C, this force, it is causing a sort of rotation or a bending moment about C. So I will write 135. How far is it acting from C? Remember, we must take the magnitude multiplied by the distance from which it is acting. So we have 4, 6, 8. So it is acting 8 meters away. Now, another thing is the sign that we're going to put here. Because it is causing a rotation or bending in the anti-clockwise direction, we decided that anti-clockwise is positive. We will put positive there. Is there another force? The 110. Now the 110 is also causing a rotation in the anti-clockwise direction. Remember that not the entire 110 is causing that rotation, only the y component. This y component is causing the rotation. The x component is acting across the plane of our point of reference, point of rotation, therefore it doesn't cause any moment. So only the y component. Now that y component will be acting 4 meters away. So we're gonna take the 110 multiplied by the component. So in this case, we'll have sine of 36.87. I'll have sine of 36.87. I'm also clear, very aware that some people prefer to use the proportion, so they would rather be, say, 110 multiplied by 3 over 5 instead of using sine. In this case, I'm using Pythagoras theorem to find the hypotenuse, which is 5 in that case, and then using those proportions to find the component. Now it is positive because it is causing our bending in the anti-clockwise direction, and that is the last one. So all of these are equal to 0. Now I'm just gonna add all these up and then move them to the other side, and then I'm gonna multiply by 12 on both sides. So I will have 135 multiplied by 8 plus 110 into 3/5, all divided by 12. Now all of this, since I move them to the other side, will be negative, so I can remove this negative, remove that negative, and then AY is equal to 112 kilonewtons. Another thing that is important to notice is that it is positive. Now because it is positive, it will be acting in, so the AX was positive, therefore it is acting in that direction, because we say positive is that direction. Here we say that also positive, we said that when a member is pushing upward, that will be our positive. So in this case, because AY is positive, that means it is acting in that direction. So we got it correctly here also. It is equal to 112 kilonewtons. Now what about CY? Now I now have only one unknown in the Y, so I can now use my forces that are acting in the Y axis. So firstly, as always, I must do the sign conversion. So I'm gonna say up is my positive. Now therefore I'm gonna look for all sum of forces in Y. They must be equal to 0. Now which forces are those? We have AY, which is 112, and then we have 135, which is acting downwards, therefore it is negative. And then we have our Y component of the 110 force. So that will be, it was acting downwards, so it will be negative 110 into 3/5. Now what else do I have? Our CY is acting upwards in this assumption we made, so we're going to put it as positive, and then that is all equal to 0. Those are all our forces that are acting in the Y direction. Therefore our CY, when you add all this up, is equal to 89 kilonewtons. It is positive, therefore our CY acts upward. Now intuitively you can see from our diagram that it makes sense why CY and AY are acting upwards, because then if it was acting downwards and only AY was acting upwards, it would cause rotation, and that is not what we are looking for. They must support this beam so that when these forces are acting on it, they can hold it in place. Now we have our 3 support reaction. Now this only took time because I was explaining, but it's actually very simple to find these values once you get into the rhythm. Now what else am I gonna look for? I'm now gonna look for my internal loading, which was the point of all this. After I find my support reaction, I then open up my beam to find the internal loadings. So how am I going to do that? The first thing I'm going to do is that I'm going to cut my beam at that point where I'm looking for the internal forces. So I'm going to have just that section. Let's take the section of AB. Therefore, I have my force of 112 here, kilonewtons, and then I have another force of 88 kilonewtons, and those are the support reactions. And then again, I will have the 135 kilonewtons, which is this force that is acting between not between but within my member A, B. And then inside here, then I will have my internal loadings. Now I will have the axial one, I will have the shear, and then I will have the moment. So let me just note them down that I have the axial one that I said I'm going to use N. I have the shear that I said I'm going to use V. And then I have the moment that I said I'm going to use M. Now, how do I calculate them now? I just use the same equilibrium formulas that I have used before. Now just at that section that I have cut up. I always forget to note here to let's just do this to show that I cut my member A, B, and this is the point B where I cut it up. Now the sum of X, always taking that right is positive. What will be the sum of X? The sum of X will be 88, which is positive, plus N, which is also positive because it is acting to the right. Now those are the only ones, so 88 plus N must be equal to 0. Therefore N is equal to negative 38. Now what does the negative mean? The negative only means that N is actually equal to 88 kilonewtons, just acting in that direction. So instead of our N going that direction, it will be acting this way, which makes sense because in equilibrium it must balance this force that is pressing on it. Now because it is pressing on it, this one must now react to that force. And in our sign convention, I say that if they are pressing on our member, we will take that as negative, and that's exactly what happened here. Now y direction, the sum of forces in the y direction, which are those? We have our 112, which is acting upwards, and then we have our 135, which is acting downwards, therefore it is negative. And then we have our v, which is acting downwards, so I will take it as negative v. They must all be equal to 0. Now how much is v? Just moving v to the other side, I can see that our v will be negative 23 kilonewtons equal to v. I just move v to the other side. Now I have N, I have V, I have my shear, and then I have my normal axial. So because it is negative, what does that mean? It just means that this direction that I had assumed that it is acting, it is actually acting opposite to that. Now, and lastly, now that we have our normal and our shear, we just have to find our moment. Now, how do we find our moment? We have the moment itself, our M, which is acting anti-clockwise. Let's assume that anti-clockwise is positive. So I'm going to take my M, my moment M, and then where else do I get moment? Now we want it about B. So we also have 135 that is acting how far from B? It is acting 2 meters away. Now because it is causing a sort of rotation in clockwise direction, the same direction as M, it will also be positive. M, remember, it is this one that I had assumed that is going anti-clockwise, but this is the sign convention that we'll use to make sure that we are consistent in all our calculations. Now after 135, where else do we get moment? Now remember that the 88 will not cause any rotation or moment because it is acting in the plane of our reference point. Now 112 though, which is our AY, it is causing some sort of rotation about B, because at this point, if B is there and we have a force, it is causing moment or rotation. I'm not using the terms interchangeably. I just need you to visualize what I am trying to explain. So 112, it is causing moment, and how far is it acting? It is acting 12 plus 4, which is 6 meters away. Now, because it is causing that rotation in the clockwise direction, it will be negative because we assume that anti-clockwise is positive. Now, we don't have any more moments, so all of this must be equal to 0. Because remember, and this is important, the sum of forces in y must be equal to 0. The sum of forces in x, or this is y and this is x, must be equal to 0. And all the sum of all moments about b must also be equal to 0 because we need equilibrium. Now, just computing this, we can find that our moment is equal to 402 kilonewtons meters.